This is Professor Brown-Cedarberg, and we're going to spend some time talking about sorting algorithms. Specifically, we're going to look at two sorting algorithms, the selection sort and the insertion sort. Now, the selection sort is a simple algorithm. It's rather inefficient. It works in n squared time, n raised to the 2. Now, a selection sort is defined this way. What we do is we start with the first element of an array, then we find the smallest element of that array, and then we swap that smallest element with the first one. Then we iterate through the remaining array. That is, we find the smallest element of the remaining array, and we swap it with the first element of that same remaining array. Here's a method that implements a simple selection sort. You'll note that it expects an array of ints to be passed into it, and we know that we can sort an array of any type. You'll see that it has an outer and inner for loop. The inner for loop consists of an if statement with an associated block of code. And in that block of code, what we're doing is we're exchanging elements within our array. So let's demonstrate this simple selection sort. So here we have an array, 5 elements long. It has the values 290, 157, 180, 285, and 168 held in it. There's our code. We've got two memory spaces, I and j. So we'll take the first step in our algorithm. We'll put into I the value 0. We'll then test, is I less than the length of the array minus 1? We know that the length is 5, so minus 1 is 4. Indeed, I is less than that. We'll go into our inner for loop. We'll give j the value I plus 1. I is a value of 0, so j is a value of 1. Is j less than the length of the array we're sorting? Yes, it is. So we go and ask this question. Is what we find at position I of our array greater than what we find at position j? I has a value of 0, j has a value of 1. At position I is 290. At position j is 157. So indeed what's in position I, 290, is greater than what's in position j, 157. So we'll exchange those elements. We'll take the value in position I, put it into the space temp. We'll then find the value in position j and save it into position I. So we'll now have 157 in the spaces I and j. We'll then take the value stored in temp, place it into the space j. We now have an array of 157, 290, 180, 285, 168. We have swapped the first two values. We'll then increment j. J now has a value of 2. We'll test, is j less than length? Yes, it is. Ask the question, is what we find at position I greater than what we find at position j? I is a value of 0, so there's 157 there. J is a value of 2, and that space is 180. So it's not true. What's at position I is not greater than what's at position j. We'll not go into the block of code associated with the if statement. We'll come back up to the top and increment j. J now has a value of 3. Is j less than length? Yes, it is. We now ask the question, is what we find at position I is 0, so in position I is 157, greater than what we find in position j. J is a value of 3. In position 3 is 285. That's not true, so we don't go into the block of code. We increment j. J now has a value of 4. Is j less than length? Yes, it is. We ask the question, is what we find at position I, that's 157, greater than what we find at position j? J is a value of 4. In position 4 is 168. What's at position I, 157, is not greater than what's at position j, 168, so we do not go into the block of code. We'll increment j. J now has a value of 5. We ask, is j less than the array to sort.length? No, it is not. So we'll go up to our outer loop. We'll increment I. I now has a value of 1. Is I less than length minus 1? Yes, it is. So we'll give j a value of I plus 1. So j now has the value of 2. I is a value of 1. Plus 1 gives us 2. We put that into the space j. Is j less than length? Yes, it is. We then ask, is what we find at position I is 1. In position 1 is the value 290. Is it greater than what we find in position j? J is a value of 2. In position 2 is 180. So this is true. 290 is greater than 180. We'll then exchange the elements. The value in I will be put into, or space I, will be put into temp. So temp now has a value of 290. We'll find the value in j, that's 180, put it into the space 1, that's I, and then we'll find the value in temp and put that into the space j, the space 2. Now we have an array that's 157, 180, 290, 285, 168. We'll increment j. J now has a value of 3. Is j less than length? Yes, it is. We ask, is what we find in position I is a value of 1, in position I is 180, is it greater than what we find in position j? J is a value of 3. In position 3 is 285. It's not, so we don't go into the block of code. We increment j. J now has a value of 4. Is j less than length? Yes, it is. We ask the question, is it true that the value stored in I, space I, that's 1, so that's 180, greater than what we find in position j, that's 4, that's 168. And it is true, so we'll exchange the elements. We find the value in I is a value of 1, so we'll put into temp 180. We'll take the value in j, put it into the space I. J has a value of 4, so we'll take 168, put that into the space I, which is 1, and then we'll take the value stored in temp and put it into space j. So now we have an array that's 157, 168, 290, 285, 180. We'll then increment j. J now has a value of 5. Is j less than the length? No, it's not. So we'll go to our outer loop and we'll increment I. I now has a value of 2. We'll test, is 2 less than length minus 1? That's true, so we'll go into our inner loop. In our inner loop, we'll give j a value of I plus 1. I has a value of 2, j therefore has a value of 3. We'll continue through this until we have a sorted array. And our sorted array will be 157, 168, 180, 285, 290. We'll execute that inner loop and then our outer loop until we meet our termination stage, or a point, and that's when I is no longer less than length minus 1. We'll have a sorted array. That's the selection sort. The next sort we're going to look at is the insertion sort. And with the insertion sort, what we do is we make one pass through the array. Each element is put in its proper place within that array. It's kind of like sorting a hand of cards. You pick up the first card and you put it in its proper place. Then you pick up the second card and you put it into its proper place in that hand. That's what an insertion sort looks like, right? In effect, what you have are two arrays, the sorted array and the unsorted. As that sorted array gets larger, the unsorted array gets smaller. Now here's a little bit about the insertion sort. It's also simple, it's also inefficient, and it also runs in O(n) squared time, n raised to the 2. Here's an insertion sort, a simple implementation of it through a method, and again you'll see that it expects to have an array of ints passed to it, and again we can pass an array of any type to it. You'll note that it has an outer loop and an inner loop. Within inner loop it has an if statement. That if statement accomplishes the swap of elements, very similar to what we saw previously. I won't walk through the simple insertion sort. I'll leave that to you to do so. So what we've done today is look at a selection sort that we know is simple, inefficient, and operates in O(n) squared times. We've also looked at the insertion sort, again simple, inefficient, and operates in O(n) squared time. These are two common sorting algorithms. I encourage you to look at them and other sorting algorithms. Thank you.